This class is on just-in-time systems. Now you'll see from the slide in front of you that this is part 2 out of 4. There are 4 classes on JIT, on just-in-time, and of course it's important that you view each of these classes to complete your study on JIT. So let's look at the JIT building blocks. Well, JIT is built on looking at the product design, the process design, personnel and organization elements. So there are 3 building blocks for JIT. The product design, it should be constructed and designed in a way that enables JIT to effectively take place. And this is part of the design of the product in the sense of the size of the product and the complexity of the product. It should enable JIT to run smoothly. If it's a large product and it requires a lot of processing, it may be difficult to fully implement JIT principles. But we'll talk about that again in a few moments' time. The process design, well, it must be possible to construct the process design in a way that enables JIT to run smoothly through the organization. So the processes should be interlinked. They should mesh with each other and facilitate smooth transfer from one process to the next right throughout the system. And of course the organizational personnel elements should enable all of this to happen. The personnel should recognize that the company is pursuing a JIT policy. They should recognize the benefits of JIT, and they should try to work alongside the philosophy to enable it to happen, to smooth out problems and make sure that the whole production system and the whole working system of the organization are smoothly linked. Let's talk about these in a little more detail. Let's start with the product design. Oh, sorry, I should mention, of course, manufacturing and planning, which I've preempted by just talking about the organizational elements. Manufacturing and planning and control, these should be structured in a way which enables JIT to function also. However, let's not spend too much time on this one, because we're going to deal with each of these in turn in the rest of this session. So we're going to start with product design. So having standard parts facilitates JIT. If the parts are bespoke or highly specialized and highly variable, then it's difficult to have standardized working practices, and perhaps machines will require tools to be changed from time to time, and machines would have to be reconfigured. So having standard parts enables JIT to happen. So the just-in-time system is facilitated by having standard parts to the product that's been produced. Standard parts enables, in a sense, standard production processes. The production processes can be then linked one with the next, so that there is continuity of production from start to finish. But it'll only happen if the parts are standard. If each order coming into the company requires some variation, that of course will prohibit the introduction of JIT. Modular designs are good, because modular designs means individual components may be combined into sub-assemblies, for example, and then assembled into the overall product at the end. So it's possible to conceive of organizations making several lines of production, all of them making components or sub-assemblies, and then at the end all of these are taken together and, in a sense, bolted together or joined together, and the finished product is the result of this. So it's a modular design, and this is what we see in car manufacturing and in many parts of industry today. We see components produced in one country, and they are produced under their particular ways of working, which may be JIT, it may not be. But the point is, they produce a component, and the component is then shipped to another country where perhaps the car is assembled. And only at that stage are all of the various components put together to build the car, to produce the car. So modular design is an attractive proposition in the context of JIT. Highly capable production systems. The production systems must be feasible for them to do this, to make the product. The production systems must be capable of producing the product. In other words, the designs, the functionality of the machines, the training of the personnel, the nature of the product, everything must come together to enable the production systems to work effectively. If any part of it is weak, then the whole system will be weak. So all of it should be brought together in a way which enables the whole system to work effectively. So the people working in the system should be highly trained, competent, know exactly what's required of them. The machines should be programmed and should be running at a pace which is appropriate given the capability of the other machines that are in the production process with it. And the product should enable the machines and the personnel to work to very high standards, very fine tolerances, but at the same time to be able to produce significant numbers in a given time period. Now the process design, well, small lot sizes will be very good, because small lot sizes means there is more flexibility in the system. It means that particular aspects of the production system are not tied up for long periods, making a lot of something, and perhaps some of these will then have to wait in the stores to be combined later with other components. Whereas if there are small sizes, small numbers required, then the machines may only work for a certain amount of time producing those, then switch over and make some complementary component which will be added to the previous one. And in this way there is a final product coming out virtually all the time. Whereas if the lot sizes are large, it may tie up a lot of capacity for long periods of time, which results in hold-ups elsewhere. Personnel and perhaps machinery further down the chain will be standing idle waiting for components to come through, all because some machines were tied up in producing large quantities. So small lot sizes, small numbers in production facilitates JIT. There is a reduction in setup time when JIT is used. The machines are in a sense set up once, and there is no need to return to alter the settings. The settings are standard, the product is standard, so the machines don't need adjustment. Then they need to be monitored in terms of wear and tear and components running out, or perhaps cutting tools might need sharpening or need some attention. But generally speaking, the setup time is reduced. The machines don't have to be switched over on a regular basis to do something else. It's all, in a sense, part of the JIT system. The machines are set up once and they run. and in running they move to the next machine. The next machine is set up once, and the next machine will process another part of the job and pass it on to the next machine, which has been set up once, and it'll process it. So it's not a question of having, let's say, 3 machines that have to be continually changed over, or X machines that have to be changed over. So we'd have machine A, B and C in sequence being set up once. Manufacturing cells, well, this may facilitate JIT. In other words, by this we mean there may be different parts of the company set aside for producing particular components. These may be viewed as sub-assemblies or some sort of modular design, some component, but there may be particular areas or cells within the company that produce particular items, and after production they may be moved manually, or they may be moved through some automated system back into the mainstream to be added to the product that's been produced. So it's conceivable within companies that there could be manufacturing cells, manufacturing areas that are in a sense working away from the mainstream, but producing items which are essential for either the completion of the finished product, the main finished product, or alternatively making something which facilitates the production itself, maintenance of the machines, for example. There is very limited work in progress with JIT. The work in progress, theoretically there shouldn't be any. The idea is that if JIT was working 100% and set up perfectly, then the components would move from one area of production into the next smoothly. There would be no waiting time and hence no work in progress. Of course, in practice there may be some waiting time, and hence some components may be waiting around for some time before they enter the next stage of production. But in theory that shouldn't happen. In theory the JIT system, if properly implemented, there should be a continuity in production right from start to finish. It should lead to good quality, because once everything is set and once the tolerances on the machines and the specifications are properly entered, then if the machines are working perfectly and if the personnel involved in the process are properly trained, then it should ensure good quality. If the quality is not good, then the specifications entered into the machines, that were programmed in the machines, or perhaps there was oversight by someone entering data, or perhaps trying to link the machines or deal with a breakdown in the machine and misconfigure the machine. But there has to be some explanation as to why the quality was not good. Otherwise, the quality should be standard right throughout. There should be production flexibility, because if the units are if the job lots, I should say, are small quantities, then it should be possible to switch over machines if need be. And modern day machines, which are broadly computer controlled, it may simply be a question of running a different program, and the machine may respond differently to the different program, and that in effect has given the organization almost instant flexibility. But the people involved in the system should also be flexible and should be trained to have knowledge of different functions, just in case something was to go wrong, or perhaps some key personnel were away ill or left the organization. So there should be some flexibility programmed in, just in case. there is very little inventory storage. There's no need for inventory at all, theoretically. The goods, the raw materials arriving in, and the goods that are coming in to the organization for processing, they should go straight into production. So there's no need to have a stores. The right quantities should be delivered. They should perhaps they have to be inspected, but they should be good quality. But they may have to be inspected. But once they've gone through that process, they can be entered directly into the production system. So there's no need to move goods from goods inwards into a store and back out of a store later. So they don't have to go into a store, be booked in, checked again, put away, and then booked out and taken out of the stores. There's no need for all of that. With a JIT system, the goods arrive in and go straight into production. So there's very little need for inventory. Now, the benefits of small lot sizes, in other words, the benefits of small production runs. Well, it reduces inventory. There are small runs in terms of production, the number of items produced. So they're not producing for stock, they're producing for orders. They're producing to meet customer requirements. There should be less rework, because if something was to go wrong on a run, let's say a run with a lot of items, a lot were being produced, and something went wrong. Let's say one of the machines was knocked off in some way, and perhaps the configuration was knocked off, or the tolerances were off. Then it could lead to a lot of bad work coming out of the system. Work which may, to save the day, to save the raw materials, may have to be put back through the system again. So there'll be less rework if the quantities produced was small in the first place. So if anything did go wrong, the amount lost would be minimized, would be at a very low level. Of course, there's less storage space, because less inventories, they're producing less of the item, less is going into stores, less waste, so less storage space that's required. And when there's a small production run, when there are small numbers in each production run, if something does go wrong, then it's more apparent. Perhaps in a large batch of items, if some were to go wrong, perhaps not all of them have gone wrong, which means there's extensive inspection costs. Whereas on a small lot run, then if there is a problem, the problem would be manifest, would be obvious from just looking at that particular run. So if the company is producing 1,000 and just a few are bad, they may go through, they may not be found. But if they're only producing 5, the lot size is 5, let's say, and there's some wrong, then it's going to be obvious that they are wrong. They're badly produced. So problems are more apparent with smaller sizes in runs. It increases product flexibility, because there's less items being produced, so the machines are able to be switched over easily from one job size and one job lot to another, and one type of product, one component or whatever. The machines can be switched over quite easily and switched back, so there's more flexibility with small lot sizes. And it's easier to balance operations. It's easier to synchronize machines and get the jobs running from one machine to the next, because there's a more continuity. There's the small lot sizes means they go from one machine to the next quite easily. Whereas if one machine is producing thousands of the items or millions of the items, then the next machine sometimes may have to wait for the next lot to come through. There may be a problem in synchronizing. So large lot sizes causes a problem of balancing production, balancing the requirements from the different machines. Machines may work at different rates. One machine may produce 100 an hour. The next machine may produce 150 an hour. The next one may produce 60 an hour. Now the problem is trying to balance out so there's no or not much wasted machine time. Trying to find the right quantities that will keep the machines running continuously. Now production flexibility, well, reduce downtime by reducing changeover time. So the machines don't have to be switched over from one type of production to another on a frequent basis. So there is less downtime on the machines. The machines are running more or less continuously. So it reduces the downtime and reduces the changeover time. It's necessary to use preventative maintenance to reduce breakdowns. So the company should have a policy of preventative maintenance on the machines. If a machine does break down and the whole system has been integrated in the way I've been talking about, that breakdown of the machine may affect many machines in the organization. So it's important that the machines don't break down and there is active preventative maintenance in place. Active preventative maintenance in the form of regular inspections and regular replacement of parts, even parts which are not broken down but are wearing out. It's important to identify which components are likely to break down in the near future and replace them before they break down. So there should be routine maintenance of all of the machines. And the workers should be cross-trained to clear bottlenecks. So the workers should have a range of skills that if there are problems, they're able to intervene and solve the issue and be able to perform different tasks, move from one task smoothly to a different task. So the workers are important because they can keep the system running. They can intervene and ensure that the system is only down for a limited period of time, a very short period of time, and they're able to perform different tasks as required. Reserve capacity for important customers. Well, some customers are clearly more important than others. So for example, a company that's making something which is going to be sold en masse through a major retail outlet in the country. Well, the retail outlet would constitute a major customer. So it's important that that customer's requirements are met. And to that end, there should be capacity in the system to meet the requirements of that customer as and when the customer says. So it's important that in addition to meeting day-to-day orders and orders from small orders perhaps from other customers, that the major customers are given special treatment to ensure that their custom will continue into the future. So there should be capacity within the system capable of being allocated to the requirements of these special customers. If they want the product varied in some way, or the design varied slightly in some way, or they want some sort of extra functionality or some extra component added on to it, then there should be the capacity within the system to meet their requirements because they are such important customers. So that concludes this session, and it's important to go back over the notes here and understand what is the nature of JIT and how these different aspects that we've considered in this session fit into our understanding of JIT, and why these different components can lead to issues if there is a breakdown, or if there is an alienation of a customer, a main customer, like I just said, or the workforce haven't got the abilities to display flexibility themselves. So it's important to have a set of notes that reflect these and be able to discuss JIT confidently. But that's all I'm going to deal with here, so let's leave it at that and say thank you for watching.